Hello, everyone. I'm Rihanna Bag, Editor-in-Chief at Machine Design. I'm so excited to be speaking to David Fritz, who is Vice President of Hybrid Physical and Virtual Systems at Siemens. So let's start at the very beginning. How would you define the term software-defined everything, this trend that we're seeing now, and what implications does it have for the future of mechanical design?
Sure. So, like many things in the technology industry, um, they don't just come out of nowhere. All right, they've evolved from other attempts, some successful, some not so successful. So the whole concept behind software defined, I've heard it referred to SDX. Here at Siemens, we define it as software defined products. Software defined vehicle, SDV, is an example of an SDP or an SDX, right? Just to clarify. Um, but it's really come out of other technologies in the past, primarily co-hardware and software development. It's come out of co-simulation. It's come out of hybridization and virtualization, and a whole bunch of things come together. But the way I would define software defined anything as that process when you're going through the development of a product, which includes the initial exploration of the product's space, both hardware and software, where the hardware can impact the software design simultaneously with the software impacting the hardware design. They both need to be malleable, they both impact each other. The days of trying to choose a system on chip from a data sheet are pretty much over because it's not possible to have a generic part sold in many, many different uh, vertical markets to get your volume up and then have it be able to handle each of those workloads equally well. So we're seeing the emergence of things like ARM's recently announced Xena compute subsystem as a way to start getting into that market. And as you might know, we've done some recent press releases with ARM where we have virtualized their compute subsystem so that software can be developed long before silicon ever exists. So that's a sort of a micro example of a software defined product because you can develop the software and it's bit by bit exact of what's going to be in the physical device that doesn't exist. And yet the software developer doesn't know the difference. It's as though he has an evaluation board with that device sitting on his desk, but it's actually virtualized in the cloud.
Okay, that's a great example. Let's move our conversation squarely onto the automotive industry.
Right.
So how does this connect software-defined products, software-defined vehicles? Let's talk about that within your context. Um, Bring us to why we're talking about PAVE 360 today.
Right. Okay. So you take the example that I just gave, and that might be one feature or one ECU. Let's just say it's IVI, infotainment, and you're trying to handle high-end infotainment. Then you bring into the picture ADAS features. So you've got several teams developing several different features, potentially on the same ECU or multiple ECUs, and then you have autonomous driving sitting on top of that, and then you have battery control and chassis control, and all of a sudden you've got this really complex system of systems. And putting all of those together before the vehicle exists is the most important way to verify that you're not going to get into this integration hell. Whereas with conventional technology, you would actually have separate tier one providers provide each of those. And then, of course, when they all come together, nothing works. And it's not really an easy task to figure out what went wrong and why it's not working. And we're still seeing to this day, virtually every OEM has massive recalls because, well, the software doesn't work. And I think my point behind being software defined is if they use this iterative CI/CD CC process that's really inherent, and you had the high level virtualization models that we're talking about running in real time, then all of those incompatibilities would have been flushed out long before you went to SOP. So that's what software defined vehicles means to these OEMs. How do I put together an ecosystem of suppliers all working off the same digital twin golden model, which is what we would call a virtualization of the entire vehicle at its current stage in a development process, which of course gets improved over time. So once each of the suppliers has access to that in the cloud, they can integrate their own, they can do their own integration testing, and all that comes together, say once a month or every couple of months. So you can go back and do system level testing of the entire virtual vehicle. So by the time you have physical hardware available, you can take out pieces of the virtualized product, put in, say, an actual ECU. The rest of it can still be virtual, and you have the hybrid, therefore the hybrid in my title. And that's the whole idea, that you do all the initial high-end scenarios. You can run millions of those in the cloud over the weekend, find out which requirements are failing. Once you reach a certain level of maturity, then you start pulling the virtualized pieces out, putting the physical pieces in, and then you use a standard engineering process to get past that integration hell.
So digital twins, for example, bring me back again to the mechanical engineering perspective. So building on this impact of software-defined excellence, shall we say? So how does Pay 360 then extend beyond your vehicle design? How does it connect to the digital twin? Tell me in more practical terms what one can expect.
Right. So the digital twin itself represents some amount, eventually all of the actuators, sensors, and compute components within the entire vehicle. Okay. So to have a holistic digital twin means several different things. There are two parts to a digital twin, as I define it. There is an executable part, which actually runs the real software that does the function of an actuator, the brake calipers, whatever. Okay, that does a physics-based model of the sensors, for example, and brings all that together. The other part of it is a declarative version of the digital twin, which is what are the requirements? Think of it as a document description of what's supposed to be happening. And it is the bridge between the declarative digital twin and the executable digital twin where the real innovation happens. And that's where Siemens and Pay 360 is the strongest in the world to date, because we bring both of those together in what we call verification threading, which allows you to make that leap from what's happening in the electromechanical world and compare that to the physical requirements. One of my favorite examples is, okay, you're designing a new car and you get a requirement that says if you're driving at 100 miles an hour on the Autobahn and it's raining and there's an object the size of a bread box 100 meters away, do you stop? The truth is, I don't know. With the digital twin, the truth is, well, I can tell you with 98% certainty, you will not stop based on your current design. So go back and change your current design. Well, it might be, okay, I don't have enough resolution in my cameras or my LiDAR to determine in the rain the size of a bread box, that it could be an object there. So what if I increase the resolution of my cameras or my LiDAR? Well, then you find very quickly that, wait, I can't transmit that much data, or I can't process it, or it takes too long to do the object detection and classification AI algorithms. Okay, so now I need to improve the number of CPUs. I need to go to a different NPU from a different vendor. I can determine all that up front to get to the point iteratively where I can say in fairly short order, yes, 98.9% chance you will stop. That's engineering. That's not throwing things together and driving it and hoping that we are successful. Very different approaches.